Hello class. So today we are talking about exponential and logarithmic models, which is in section 4.6. So the basic premise is that things in life grow or shrink, and we can model this in different ways, but like one of the most common way that things grow is exponentially. And so that's what we're going to learn about today. But first, we need to learn about a very famous number that we haven't talked about yet. And it's very related to exponential growth. So this famous number is called E. And it's roughly 2.7 something. Okay, so I'm not going to try to guess more digits than that. But the idea is it's between 2 and 3. And it's extremely related to exponential growth. And here's one way to figure out the number. So what we're going to do first is we're going to figure out where this number comes from. So where does E come from? So we haven't used it yet, but it's going to show up a lot now, so we got to know where it comes from. So here's one way to make it show up. So suppose you have $1 to start with, and your bank decides to give you 100% interest in 1 year. So in 1 year, you get 100% interest. So how much money do you get then? So you have your dollar plus 100% of $1 is 1 of $1. So you get 1 plus 1, you have $2, yay. But then you think, I want more money in that year, so I find this other bank, a better bank. They say, okay, I'll still give you 100% over the year, but I'm going to say it differently. I'm going to say, I'll give you 50% twice instead. So every 6 months, you get 50% interest. So how much money do you get then at the end of the year? Well, you still have your starting dollar, and then 6 months into it, you get 50% of that dollar. So you start with this, and this is like 6 months later, and then another 6 months go by. How much more do you get? Well, it's a bit trickier. You get 50% of how much you currently have. So how much you currently have is this amount on the left. So that entire amount, which is really just $1.50, but I'm going to write it like this, is being multiplied by 50%. But another way to think about it that's much simpler is $1 plus you get 50 cents at 6 months, and then you get 50% of that amount. So what's 50% of $1.50? That would be 0.75. Half of $1.50 is 75 cents. So now you're up to $2.25. Oh, so actually you get a little bit more this way than up here. You only got $2. So now you think you're onto something. You say, aha, I'll just keep doing that type of thing. So let's do another bank says something else. So instead of doing 50% twice, and then we're going to grow up and not use percentages, we're going to use fraction. We're going to say 1/3, or 50% we were thinking of as a half, really. So now we're saying 1/3 3 times instead. So now what we have is we have our starting dollar plus 1/3 of that dollar plus 1/3 of that previous amount at the next third of the year. But then on the next third, we get to do this 3 times. I get this whole amount. In there. So I get to do a third of each previous amount. So it sort of looks like a whole bunch of stuff going on. And so then this is how much you end up at the end of the year. But it looks really complicated, but it turns out to simplify into something much easier. It just turns out to simplify into 1 1/3. So what's 1 1/3? 4/3. 4/3 to the, sorry, let me verify something. 4/3 to the 3rd power. And up here, this was actually 3/2 to the 2nd power. So when you do this pattern, when you do this type of interest growth, you get a pattern going. So you might not see the pattern. But then, so this is how many dollars you would get, and that's going to be a little bit more than 225. So then if we do like a fourth, every 4th of the year, so you get a 4th of what you have 4 times as interest, then what's going to happen is you're going to get 5/4 to the 4th dollars. And you can put that in your calculator, and it's roughly like 2.4414. And then you could keep going. So if you jump all the way to like 12, then you'll end up with 13/12 to the 12th power, and that'll be like 2.61, something like that. So the pattern is that if you, however many times you do it, that's how many times you multiply this number by itself. And the number that you're multiplying by itself is always 1 more divided by that amount. So here, if you get interest 12 times in the year, so this would be like once per month, I guess, and you do it, and you get 1/12% interest, then you end up with this. And so then you keep doing this pattern. So let's say like you got it every day, so that would be 365. Then you would get something like this, 366 over 365 to 365 power. If you put that in your calculator, you'll end up with 2.714 ... And what's happening is that this number is not growing any bigger, really. It's just getting closer and closer to E. So remember at the start, I said E is roughly 2.7 something. So E, what it really is the end of doing this pattern forever, which we haven't learned how to do in this class. That's in calculus. But doing this pattern forever will get you closer and closer to E. So E is the limit of this process, is what it's called. So that's the idea. So if you start with $1 and you get interest infinitely many times, in this way, in the above way, then the amount of money you end up with is E dollars. So it's a little bit confusing. This is just how you define E in the first place. So you don't really need to know how to figure out what E is. I just want to give you context. So this is where it comes from, and it's going to show up a lot. And it's very related to growth. So just think about it as roughly 2.7 something. It's between 2 and 3. And then what people do is they use it for a function. So they say e to the x. So we've done exponential functions like this before, but with whole numbers like 3, 4, 5, 2, or whatever in place of e, and we use it a lot. And the idea is that this function grows exactly at any x value equal to its own value. So very strange thing. So the idea is that if you want to know how fast it's growing anywhere, it's actually growing at the rate that it actually equals. So the idea being, we've seen how to graph 2 to the x and 3 to the x, and they all sort of look like this. And then we've seen that they grow very fast. And so they vary like in how fast they grow just ever so slightly. So they look maybe like that. But then there's E is like in here somewhere perfectly. And how fast it grows is exactly its value at any point, which is a super weird property. So the idea is something like, if you want to know like how fast does this guy grow, well, we learned about this thing called average rate of change a long time ago. So you'd have to do its average rate of change, where you do the y value minus the y value over the x value minus the x value. And you would get something, but you would not get exactly its own value. So what I mean is, if I just want to know like at x equals 3, how fast does it grow when I get to 3? For this guy, you can't just like plug in 3. That's not right. But for e to the x, this actually turns out to be exactly the answer. So it's got lots of other weird properties, but I think I've already said too much about those, and it's just going to seem very confusing. The actual problems that we deal with are not going to be so bad. Okay, so let's move on to those things. All right, so here's where it shows up for our word problems. Given an amount of stuff, so what is stuff? It could be population of people, it could be like an amount of bacteria, an amount of radioactive stuff. But the point is, if it's any sort of stuff that can grow at a rate proportional to how much there currently is, proportional to the current amount of it. There's too many R's in that word, current amount. of it. So how much it grows equals some constant number times the current amount. That's what this all means. Then the amount at a later time, so you like have 100 of something right now, you want to know how much there is later. So the amount at a later time is modeled by exponential growth. Or if it's decreasing, if it's shrinking down, decay instead. And it's always modeled by, in that situation, this function. So A is going to stand for the amount after some time. Okay, so that's what this means. On the left, so this is just saying that the amount you have at a later time, so maybe the time is like 30 hours later, then you would plug in t equals 30 or something like that, is equal to some starting amount. So this is times e, this fancy new number I just explained for a long time, to the power rt, where t is still the amount of time passed, and r is just some number that we usually have to figure out. Okay, so this is what we're going to be using a lot. And so let's just jump into a problem. So radioactive isotopes are one of these things that grow proportional to, or shrink proportional to how much there currently is. And in this situation, they decay. They decay exponentially. So what this means is that the amount of the isotope is equal to the initial amount times e to the RT. So this equation applies to this situation. And what we can do is we can do something called finding the half-life. So what happens is you have radioactive stuff, and as it decays, you want to know how long it takes until there's half of the starting amount. That's what half-life is. So that's what we can do. We can use this to find something called half-life. So this is how long until the amount is half of the initial. In other words, what's half of the initial? That's going to be 1/2 times c, because I said c is the initial amount. Okay, so here's a more precise example. Bismuth, I don't know anything about radioactive stuff, but apparently bismuth-210 is one of these radioactive isotopes, and it decays 13% a day. So we want to find the half-life. What that means is we will have to eventually solve for t. And which time are we solving for? Which t are we solving for? We're solving for the time corresponding to the amount being 1/2 of the initial. That's what finding the half-life really means. So at the end of the day, we have to be solving for a time. That doesn't necessarily mean that's how you start the problem. That's just how the problem will eventually end. Okay, so in the later examples, everything will be more clear because it'll be more methodical. Right now, we're sort of just thinking on our feet and figuring stuff out. So don't panic yet. Promise it gets easier. Okay. So let's see. So what can I do right now? Well, all I know is that this thing decays 13% in 1 day. So that means what? Let me do some sort of color corresponding. So that means that after 1 day, I know how much amount is left. I know that there is, if 13% is gone, that means 87% is left. So 0.83%, aka 0.83 times C, amount left. So what's going on is that we're saying that if I plug in 1 to this equation that I'm using to model the situation, if I plug in 1 to there, I can automatically say that the left side actually equals 0.83 of the initial. So then I end up with a situation like this. And then r times 1 is just r, so I can leave it like that. And what this will allow me to do is solve for r, because I can divide out the c's on both sides. And now I'm at this sort of situation. And now this is an exponential equation to solve, and we know how to solve these. What do we do to bring the r down? We log both sides. But we're going to do, to make our lives easier, we're going to do log with the base that matches the exponential. So we're going to do log base e. So e is just a number. It's not a variable. It's a fixed number, right? That's what we figured out at the beginning. So I can do something like this. And then I just get r. Whoops, I'm doing that on both sides. So log base e on both sides. And so that lets me solve for r. But then a very quick note is that this number e is so special that actually log base e, what we do is we give it its own notation. We call it ln of e. Sorry, ln. And we don't write a base. That just means base e. Because e is such a special number, it's called the natural log, because e is like the most natural number to use for exponentials, I guess. So the log that has the base as e is called the natural log. Okay, so really, and then you'll see this number on calculators. You'll see this button on calculators, ln. So ln of 0.83, that's what r is. And so the idea is that this little equation up here models any old exponential growth or decay, but to apply it to our situation, we actually have to know what r is in most cases. So now we do. So now the decay amount of our bismuth 210 is actually this. And if you want, you could put ln of 0.83 in a calculator to estimate, and you'll see that it's a negative number because the rate, that's what r stands for, should be negative because the stuff is decaying in this problem. Okay, so now we can find the half-life. And how do we do that? Well, that's what I said at the beginning, way up here. We should be solving for a time because it is an amount of time that has passed. But what we're really doing is we're setting a of t equal to half the initial, 1/2 c, and then solve for t. So if I just put that there, I end up with this. And now I'm in a situation where I can solve for t because the c's again are going to cancel if I just divide them out. And the e and the ln, because the base is the same, the base of the log is the same as the base of the exponential, there is some sort of weird cancellation, but you might get confused if you try it like that, so don't worry too much about it. I'll sort of do it the long way. But in any case, this is what we can solve for t. And notice I didn't even need to know the initial amount to solve for t. So that's interesting. The amount of time it takes for there to be half of what there used to be does not actually depend on the current amount or the initial amount. Okay, so I can solve this guy for t. I need to bring the power out, which means I have to ln both sides. So I'm going to use ln because I want to use base e as my log so that this ln and this e will very nicely cancel each other. But you don't have to use base e, but it's the easiest. So then the idea is that these guys cancel and you just get what's left in the power to come down. And now to solve for t, I just have to divide that over, and then this is your answer. So you could plug this into a calculator and it'll give you an amount of time. I forget exactly how much I didn't estimate it, but that's it. Okay. So that should be that. Sorry, I'm just checking something out. All right. So let's move on to the next problem. So that was sort of a lot to take in, but we'll do the next one and it'll be very similar and you'll see sort of how the process always stays the same. All right, so here's another one. Carbon-14 half-life is 5,730 years. So what we're gonna do is we're gonna figure out how old a really old bone is. How old is a bone if it has 20% of the initial carbon-14? So whenever you see these word problems, what we're always doing is we're either solving for a time or an amount. That's really what it always comes down to. So in this case, we're solving for a time because it's asking how old is this thing? So we're going to figure out a time in the very end. But the main thing is that because it is a radioactive isotope and we're talking about half-life, we're going to be using this same equation to model how much is left after whatever time you want to plug in. So this tells you how much is left as long as you know R and C, which we don't yet, but maybe we'll get them. Okay, so in this situation, I'm going to be wanting to solve for T at the very end when the amount is what? When the amount is 20% of the original, of the initial. So that means at the very end, I'm going to be setting the amount equal to 0.2 of the initial, 20% of the initial. Okay, but that's at the end. And I can't solve that equation yet. If I try to solve this for T, whoops, what was that? If I try to solve that for T, why can't I? So I could still cancel out the C's, but since I don't know what R is, I won't be able to get T alone. So first we need R. And these problems always give you a way to figure out what you need. And the clue this time is that the half-life is already told to you. We don't have to figure it out, it's told to us, but we have to use it. So the half-life is 5,730 years. So what does that mean? You should always be thinking about, like, what do these clues actually mean? What do they actually tell you? This means that when you plug in the amount of time being 5730, that the amount of stuff is going to be half of the initial. So what we can say is that when I plug in 5,730, on the left is going to be half of the initial. And on the right is just the formula where now I've plugged in 5,730 for time. And then this I can solve for R by doing the ln thing again. So I just ln on both sides. And then that allows me to bring down the power and get rid of this, because the base of ln, remember, is e. So I'm doing, the log is matching the exponential. So they're just going to cancel out to 1. And then to solve for r, I just have to divide by 5730. So that's r. So now that I have r, I can just put it up here, and that'll let me solve the problem. Okay, so then to finish solving, I need to know, when does this happen? What amount of time makes the left side be 20% of the initial? And now that I know that this is r, I can figure that out. So I can divide out the c's again. And then I can ln on both sides, so that on the right side, the ln and the e just cancel, so the power comes down very nicely. So all I have is the power left over, which was all this stuff. And then to solve for t, I just got to multiply across and divide the ln of 1/2. Right? So that's it. And if you put that in your calculator, you'll get some amount of years. I think like 13,301 roughly. So you can test that out if you want, make sure you get it right. Okay, good. So what else? So those are decay problems. Now we are going to talk about growth problems. So for decay problems, you really care about how long it takes for something, for there to be half left. That like comes up a lot. For growth problems, usually you're given usually you're going to be talking about something called doubling time. Which is similar to half-life, but it's really like how long until there's double. Which means how long until this amount on the left is actually 2 times the initial instead of 1/2 of the initial, because things are growing instead of shrinking. It should be going up to double as opposed to going down to half. So here's one example. So since the Industrial Revolution, the world growth rate is 1.14%. So let's find, in that situation, how long it takes to double the population. So in this situation, we are using our little growth model to model population amount. So we're still using this equation, but now this amount, it's not like an amount of bacteria, it's an amount, it's a population. Population after some amount of time has passed. But it still grows or decays in the same way as bacteria or radioactive isotopes do. Okay, so if I want to find the doubling time, that means that I want to be setting the amount to be double the initial, which means 2 times c. And then I want to be figuring out what the time is, but I don't know r, so I can't do that yet. So where do we find R? That's probably going to come from the growth rate. So that is exactly what happens. That the growth rate being 1.14%, what they're telling you in that situation is exactly R. You don't actually have to figure anything out in this problem. R is 0.0114. So this problem is much faster than the other ones because you don't have to solve for R. They're just telling it to you. So what we have to do now is solve this guy, 0.0114 t for time. So again, I can divide out the c's. And then I can log both sides with the base e so that the one on the right vanishes very nicely. And then to solve for t, I just have to divide. So if you plug this into a calculator, this will be roughly 60 years. So it only takes 60 years for the population to double. Not too long. And again, it doesn't even depend on C. It doesn't matter what C was because I didn't even need to know what C was. It still worked. So here is another one. What about bacteria growth? So bacteria also grows exponentially. Which means, again, I can use this equation to model how much bacteria there is at various amounts of time. But in this problem, we are going to be given different information. So this time we're going to suppose that the initial population of the bacteria, so how much bacteria there is 2,000. I don't know what units of bacteria are, but units are for physicists anyway, so who cares? So there's 2,000 somethings of bacteria. And 1 hour later, there is 2,500. So let's find the doubling time. Once again, because we are finding the doubling time, we're really gonna, in the end, be solving for t in what situation? When the amount is 2 times c. But we don't yet have r, so we can't do that. Okay, so now we have to use this information to find r. We're not just given r immediately. And this information is a little bit different than other ways we've solved r. So what we're going to do is we're going to know that this means that c is 2,000. C is the initial amount. It also corresponds to plugging in t equals 0, and you can check that out yourself. If you plug in t equals 0, you get e to the 0 is 1, so you just get c left over. So a of 0 we're being told is 2,000, and that's just c e to the 0, which is just c. So this lets us solve for c immediately, and then the other piece of information we're given, the 1 hour later, what that is telling us is that when I plug in 1, the amount at that time, 1 hour, is 2,500. So c e to the r times 1 gets me 2,500. And because I now know c is 2,000, I can plug that in there. And then I can solve for r. So I divide over the 2,000, I got 25 over 20, e to the r. What's that, 5/4? And then I can log both sides with my base e, meaning I do ln on both sides, and I get that. So that's r. So now I'm ready to solve this thing because now I know what r is. It's ln of 5/4, right? That's what we said there. So now I can divide out the c's just like always. And then I can log both sides to get rid of that e there. And then I can divide out the numbers in front of the t, which is just this ln. Oops, should probably divide it over like I said I was going to. And then that's it. So that is the doubling time. Okay, so that's gonna be it for this video. I will see you next time.